OK, good. So the setting that we want to consider is that we have some weak computational device, a smartphone, a weak laptop, a smartwatch nowadays, that wants to perform some expensive computation. And it can't afford to perform this computation by itself. So the natural solution is to use the power of the cloud, some powerful external server, to do the computation for us. So our laptop sends its input x to the cloud, gets back as a result y, which is equal to f of x. Problem solved. The only problem that remains is that we don't want to entirely trust the cloud. So the cloud may be sort of actively malicious. It may even just be lazy, just sends back 7. So we don't want to just blindly trust the cloud. And since we don't trust the cloud, there are multiple security concerns that arise. But I think the two most fundamental ones are, first of all, just verifying correctness. Right? So we're afraid that the cloud is, say, lazy or even malicious. Why should we trust what it's saying? The second issue is, if we don't trust the cloud, how can we share our secret data x with it? So the focus of this talk is only going to be on the correctness aspect. So we think of x as being publicly available. And what we're really worried about is verifying the correctness of the computation, that indeed y is equal to f of x. And this leads to the notion of a doubly efficient interactive proof. This was introduced in a work of Shafi, El, and Guy. And the idea is that we want to allow the client to be able to somehow verify the correctness of the computation by itself, using the help of the prover. Of course, the naive way to do that is just to compute f of x by yourself and compare to y. But that really, doing that means that you don't save anything. Right? You are in fact computing f. That's useless. What we're looking for is what we call a doubly efficient solution. So we want the verifier to be extremely efficient. In particular, much more efficient than the time that it takes to compute f by yourself. And we also want the prover to be relatively efficient. So we're not looking for solutions in which the prover runs in some exponential time. We want to do this for problems in which the prover is also, say, polynomial time. So relatively efficient. A third aspect that we want to minimize is the amount of interaction. So we prefer protocols in which we don't have a lot of communication going back and forth, a lot of rounds of interaction. So just to compare this notion to the classical notion of an interactive proof, so also in interactive proof, we have this situation of a prover trying to convince a verifier of a statement of the form x belongs to a language L. But in the classical setting, we allow the verifier to be polynomial time, any large polynomial, and the honest prover can be unbounded. Right? The setting that I want to consider here is where the verifier is really efficient. Say it basically more or less just reads the input, so linear time. And I want the honest prover to be polynomial time. I'm not talking about what power I'm thinking of the cheating prover having quite yet. OK, so let's be a little bit more formal. So we have our verifier, we have our prover. And we want to have the following conditions. So they interact. And when x belongs to the language L, as usual, we want completeness. So let's say that the verifier accepts probability 1, so perfect completeness. If x doesn't belong to the language, here I really want statistical soundness. So no matter what cheating prover you give me, with high probability, or let's say with probability half, the verifier rejects, and you can amplify this by repetition. So far, this is very similar to an interactive proof, but the efficiency requirement, as we said, is different. So we want the running time of the verifier to be, say, quasi-linear, and the running time of the prover to be polynomial. Okay, so that's a doubly efficient interactive proof. So let me tell you what's known about this. So in this result of Goldwasser et al., they gave a construction for any language that can be computed by a bounded depth circuit, more specifically by log space uniform NC circuits. And the number of rounds really grows with the depth of the circuit. So it does require quite a bit of interaction. A second sequence of results are also results that are not listed here are in the setting of computational soundness, where you think of the cheating prover as also being somehow computationally limited. In particular, it can't break crypto. It can't factor integers and so forth. So in that setting, a classical result of Kilian gives a 2-round protocol for any language in NP, based on a fairly standard cryptographic assumption. And in a recent work with Yael and Ran, we gave a 1-round solution for languages in P, based again on a fairly standard cryptographic assumption. But the setting that I want to talk about today is more the GKR setting. So statistical soundness, we're considering any possible cheating strategy without thinking of any computational limitations. So our main result is the following. we show that every language that you can compute in polynomial time and some bounded polynomial space, so some n to the delta for a sufficiently small delta, for any such language, we give a constant round interactive proof, also public coin, and it's doubly efficient. So the verifier is linear time or almost linear time, and the prover is polynomial time. OK. Should I parse something that's, I think, OK, so this is sometimes called the d-time space poly n to the delta. It contains in particular the class SC, which is polynomial time and polylogarithmic space. OK, so this is sufficiently small. Sufficiently small. OK, so I'm going to tell you more about the proof of this result and about this result, but let's see how tight it is. So let's define the class IP subscript DE as a class of languages having such doubly efficient interactive proofs. What our result shows is that this class contains this class d-time space, so time poly n space n to the delta. This is our main result. It's obvious that this class is contained in the class P because both parties are polynomial time. So what can you do more than that? And it's also not hard to show that this class is contained in space, in linear space. The reason is that if the verifier is linear time, that means that also the communication is linear. And you can at least intuitively try to simulate all possible messages from the prover in linear space. OK, so kind of two gaps here between these results. One is the delta. So we'd like to get delta up to 1. And the other is kind of this annoying fact that this is like one Turing machine that runs in bounded time and space. And here we have sort of one Turing machine for time and the different Turing machine for space. But in spirit, I think it's somewhat tight. OK, and I think it's also going to be beneficial to see. Is there a question? No. So I think it's going to be beneficial to see what exactly are the parameters that we get for general languages, not just for languages sort of within P. So if you assume you have some language that you can compute in some arbitrary time t and space s, what parameters can you get? And so let's fix some small epsilon. Think of epsilon as how much you want to speed up. So you could compute this by yourself in time t. Now you want to compute it in time t to the epsilon. What can you do? So we can indeed do this. So we can obtain an interactive proof. The verifier is going to run in time t to the epsilon, like we wanted, this sort of speed up. So that's this factor. And then over here, think of this as just, at least if t is small, this is basically reading the input. Morally, this is reading the input. The prover roughly runs in time t, like we wanted, so not much more than the time that it took to compute the language. The communication, again, we can shrink it up to t to the epsilon. But we need to pay for epsilon somewhere, and that's in the number of rounds. So it's going to be roughly exponential in epsilon, in 1 over epsilon. OK? So we believe that in terms of this dependence, there needs to be a dependence on epsilon. We can discuss it. Maybe tomorrow I'll say more about that. But we don't see any reason for it to be exponential. So it may be possible to do this with polynomial dependence on epsilon. OK, so I said here that epsilon is a constant. We can do slightly less than a constant, but let's not get into that.
So this implies also.
Yes, this is a strict generalization. So
if it is poly n.
Exactly. So if t is some large poly n, I'll set epsilon to be like small enough to kill that poly. OK, so before telling you about the proof, let me just mention sort of that this kind of improves on 2 aspects of previous results. So on one hand, we show that this class IPDE is larger than was previously known. So not only does it contain bounded depth circuits, this was known via GKR, but it also contains bounded space circuits. And this is even disregarding the fact that we get constant rounds. So this was not known even without constant rounds. Secondly, if we do focus on constant rounds, then these protocols were really not known. They were basically only known for NC1, so not even for log space. And that's even if you allow you an unbounded honest prover. So a constant round is kind of a big improvement.
What happens if you are trying to do the same for a language that has a probabilistic algorithm?
It's fine. So the first thing that the verifier would choose its coins, send them to the prover, I think.
But it may be many more coins. linear. I mean, if the running time of the
I see.
computation is t, it may
Right.
be t.
Yeah, I need to think about it. I'm guessing that it should work, but I need to think more carefully. I'm not entirely sure, but I think so.
Also, you mentioned that you get a public coin. Is it an issue?
So there are general transformations from private coin to public coin, but this transformation transforms like an efficient prover to an inefficient prover. So it's sort of important to, I mean, if you care about the fact that it's public coin, and you should care, it's useful for a lot of applications. You can't just do the general Goldwasser-Sipser transformation.
It is an issue.
In what sense?
So, if you, I mean, you can.
Yeah, you can't do the generic transformation while preserving an efficient prover. And I would say that public coin is an important property for some applications. In particular, these applications, so I want to mention a few corollaries. So these are corollaries of our main result. So the first thing, which has been of interest to people, is obtaining zero-knowledge proofs for NP languages in which the communication is kind of directly proportional to the witness length. So without going through the entire NP completeness machinery, so we get such such interactive proofs for NP, zero-knowledge interactive proofs for NP statements, as long as you can compute the witness relation in some bounded space, so polynomial-time in some bounded space, like in our main result. A second corollary is obtaining constant round interactive proofs of proximity. I don't want to go into details of this, but these are somehow interactive proofs in which the verifier runs in sublinear time. But the soundness guarantee is weaker than the normal one. The third corollary is, even if you don't care about bounded space computations and you really insist on bounded depth computations, then we can somewhat strengthen the GKR result. So there they needed log space uniform NC circuits. Using our result, you can extend this to sort of bounded space uniform, so n to the delta uniform NC circuits. So you have more flexibility when using the GKR result. OK, so let me tell you a little bit more about the proof. So let's fix some language where we can compute in time t and space s. Think of t as a large polynomial, s as a small polynomial, or polylogarithmic maybe even was useful. And think of the Turing machine computation on the Turing machine that does this. So the Turing machine starts at some initial configuration, so this point, and does the computation until the end. It's a tableau of the computation. So it's width s and has length t. Our goal, recall that our goal is to construct an interactive proof for this language L, in which the verifier runs in time that is much shorter than t. OK? So here's a naive idea. Let's have the prover specify some k sub computations or sort of k configurations of the Turing machines at like every t over k steps. So the configuration that the Turing machine has at time t over k, at time 2t over k, 3t over k, and so forth. Okay, so it specifies these k configurations by just sending them to the verifier. Each one of these subcomputations you can compute by yourself in time t over k and space s, right? So they're in d time space t over k s. So the first naive idea is, why don't we just sort of recursively assume that we have interactive proofs for these problems and recursively run all of them? Okay, so we're trying to build an interactive proof for this d time space ts. Let's assume that inductively that we have these we have interactive proofs for these type of languages, and just recurse on all. So that's a nice idea. The problem is that it sort of, if you open up the recursion, you're actually going to look at each individual step here. Right? So recursively open up, or if you open the recursion, you see that it takes time even more than t. So that's really not what we're looking for.
You are not using the prover.
The prover is specifying the right. It's just telling the entire thing. Yes, it's sending the entire thing. So that's not good. OK, so let's try a different naive idea. Let's have so the prover still specifies the k points. Now let's just choose, sort of do a spot checking, choose a few of these subcomputations at random, and just recurse on those. So that doesn't work so well because, or not well at all, because if you can think of a sort of an input that is not in the language, you do the correct computation until some random point. At that random point, you do whatever you want to do, some like illegal step, and then you do some other computation that leads to an accepting state. So unless when you do the spot check, you choose the place in which the prover sort of was cheating, you won't find him. So this has terrible soundness error. Okay, so no good. What we'd really like is kind of the best of both solutions. If we want to be able to verify all these k subcomputations, so like in the second solution, we want to do it much better than just doing k-independent executions, but we want to do this with good soundness or small soundness error. So that's what we'd like. So here's the hope. So suppose that we have a language that has interactive proofs with complexity. So you think of this as the verifier running time or communication, whatever you like. So we have this language that has an interactive proof. We want to construct an interactive proof for verifying sort of k instances simultaneously. And we want to do this better than the naive solution, which is just running the interactive proof k times. Okay, so that's the hope. And we get pretty close to achieving this, good enough for our application. We'll see exactly why. So we can do this for a specific type of interactive proof. And we call this process amortizing interactive proofs. The reason is that sort of, if you can do this, then the cost per instance really goes down with k. Right? So the cost is much less than k times c divided by k. The cost per instance is very small. So this is called amortizing interactive proofs. And this is going to be the focus of the talk, how to do this kind of thing.
So there's no direct sum in this particular
yes.
interactive type of
Yes. Or there's a positive direct sum. I don't know.
direct sum means that you cannot.
That you cannot? OK. OK.
I mean, that's how we
OK.
all play just
OK.
one.
Actually, since you brought it up, then no, I won't say that. OK.
In the GKR proofs, the amount you need to pay is proportional to the depth of the circuit, right?
The amount in terms of like you're talking about rounds, or are you talking about
Whatever. I think everything is dependent
Sure.
on the depth.
Yeah, in particular the rounds.
But if you have many copies, that the depth is the same, right?
Yes.
So isn't it? Why is it immediate?
So if you have so the thing is
So the circuit for the whole thing has the same depth as
Yeah.
the one component.
It's not the cost here is not the depth. The cost here is the time. How do you get the time not to multiply by 2?
The thing is that what you're doing would be an amortization sort of for, you have the circuits and you want to like amortize them. Here I have interactive proofs and I want to amortize, not the circuits. I think you have good intuition. This was sort of the intuition that led us to the solution. You're saying if I have k circuits and I want to check all of them simultaneously, let's look at the circuit that computes their and run GKR on that. That would be like the cost of a single circuit.
Yeah, but you can take the same circuit and just multiply, just have it k times.
Sure, that's what I'm saying. Take the circuit that you're interested in, take k times and compute the and of that.
Yes.
Use GKR on that.
Yeah.
So that would show that you can sort of you have like this language that you can compute by a small depth circuit or any circuit, and computing k copies of that would take you roughly as much time as just a single copy.
Yeah.
But here I want to assume that my starting point is not a circuit, it's an interactive proof,
I see.
because I want to do this sort of recursively.
So this is more general. You don't know how this
In a sense,
interactive
yes.
proof was constructed.
Yes.
I'm giving.
Yes.
What I suggested is just one way of getting it.
Right,
No, he knows how it will be constructed. They will construct it in
No,
a
you
way
don't.
that it will be doable.
yes.
No, the original interactive proof, so there is an interactive proof for one copy. This you don't know how it was constructed. You don't know the underlying thing.
I mean, it would be open up from our
You
recursion.
don't know how like the original circuit was transformed into interactive proof.
But
You
Right.
can take this
they
interactive proof and
I mean, I will know it, but I won't need to. I will control it, but I won't sort of need to. It'll be, OK, but is this idea of amortizing interactive proofs, is that clear, more or less? OK. So let's start off, rather than showing how to amortize interactive proofs, let's start off with a simpler task, which is amortizing NP statements. OK? What do I mean by that?
Amortizing written proofs.
Sure. Yes. OK, so this is the following sort of clean problem. I have a prover who has as input statements x1 up to xk and corresponding witnesses w1 up to wk. Let's say that these witnesses are of length m. And I want to construct an interactive proof to convince the verifier that all of these statements are in the language with communication that is shorter than just sending all of these k witnesses. OK, I want to do this interactively. So this is amortizing written proofs. And we can't quite do this. So we don't know how to do this for general NP statements. And I think it's a very interesting open problem. We can't do this for a special subclass of NP statements, those having unique witnesses. And that's what I want to show you. OK, so this, let me briefly remind you of the class UP. So UP is exactly this restriction of NP in which for correct statements, there exists a unique accepting proof. OK, the canonical example for that is unique SAT, which is a promise problem. So it's either a formula that has exactly one accepting assignment or unsatisfiable. OK, so this is the class UP. And what I want to show you is how to amortize UP statements.
Why does this suffice?
So it doesn't suffice as is. So we'll need to somehow generalize this to amortization of some U interactive proofs. Some notion of that will come up later. And that will somehow be enough. So this is kind of a warm-up you can think of.
So there is a way to turn any language
To the
output with the k.
So I haven't told you what the notion for interactive proofs is. And there it's not. I don't need it. So I'll keep it so that all of my interactive proofs are always with this special property. OK, so this is what we want to show, that for the class UP, we can do this type of amortization with what kind of parameters? So let's see, first of all, communication. So the communication is going to be sort of, rather than the k times m, which is the naive thing, it's roughly k plus m. OK, a little bit more than that. So significant saving. Verification time is k times n is just reading the n inputs. Right? So the verifier seems to make sense that he has to read the input. And on top of that, it's just some polynomial in m, some log k factors as well, rather than the m times k that the naive thing gets. The prover, what can you do? It needs to run, compute all of these things. So it's poly m and k. And the number of rounds, at least as I stated here, is going to be log k. OK, so this, as is, won't quite be enough for our constant round interactive proofs. We want the rounds to be, so k is not going to be constant. It's going to be a little bit more than that. But we can, also in this result, we can trade off getting less rounds with higher complexity throughout. OK, so we can get sort of constant rounds here. And everywhere you see a log k, it will be some k to the epsilon. OK, so this I want to show you. I hope, how am I doing on time?
You started late.
Yeah.
You have about half now.
OK. OK, so that's what I want to show you, how to amortize these UP statements. And again, we're going to try with some naive solutions, and slowly we'll get sort of less naive and more working. OK, so here's our situation. We have our prover. It gets the k statements, x1 up to xk, k witnesses, w1 to wk, and the verifier gets the k statements. And the prover wants to convince the verifier that all of these languages, all of these statements are in the language. So the first thing that, so now it's going to be, I'll need to help you a little bit. So the first thing that the prover does is to compute PCPs for all of these k witnesses, all of these k statements. Just to remind you, a PCP is an encoding of an NP proof, which you can check by just looking at very few coordinates. OK, so the prover computes PCPs for these k statements. And he's going to put them, you can't see this, but he puts them in a matrix, which I'm going to denote by A. OK, so this, I guess, k by some poly m. So the PCP encoding increases the size a little bit. So k times poly m matrix.
You could do quasi-linear, but you don't care about
Right.
poly m is fine.
Yes.
Okay.
Right. I also need to be careful because I'm going to need some of these properties of the PCP, but not too much. OK, so what does the verifier do? So the verifier is going to generate PCP queries for these PCPs. And I'm going to use, here's one property of the PCP that I want to use. The fact that the PCP, the queries that you do into the PCP don't depend on the input. So this is a specific type of PCP in which the verifier first generates its queries. It gets back the queries to the PCP proof, gets back the answers, and only then looks at the input and decides whether to accept or reject. And we have constructions of these type of PCPs. So the verifier generates these queries. These queries are, in a sense, good for all of these statements because the query locations don't depend on the input. Now we're going to send over to the prover.
PCP queries for each one of these statements?
No, I did once. Because the location of the PCP queries doesn't depend on the input, they're in the sense.
So you're going to, they will be the same location in all
Yes.
the rows.
Yes. Yes. So.
Just losing a factor k in the sum.
Right, but it's going to be important later on.
Okay.
So my verifier sends over these queries to the prover. These queries specify sort of columns in the PCPs. Right? So for every PCP, specifies some location, but I'm using the same queries for all. So these, say, 3 columns. And the prover sends back the restriction of the matrix A to these columns. Okay, so basically answering the PCP. And the verifier, what can he do? He just checks that the PCP verifier for each one of these rows accepts. Okay, so that's the first naive idea. So it has some good things going on. It has some bad things. So it's, to be positive, let's start with the good thing. So this is extremely efficient, right? So the amount of communication, let's say, is just k plus log m. So very, very efficient. The problem is that it's totally insecure. The reason for that is that soundness for PCPs is only guaranteed if the PCP is sort of written somewhere in advance. And if I get to see, if you get to see all of the PCP queries and then answer, it's very easy to fool the PCP verifier. And this is exactly the situation that we're at. So a cheating prover, what does he get? He gets these queries queue. You can very easily come up with answers that would satisfy all of the k sort of PCP verifiers. So that's not good. And the problem seems to be that the cheating prover was totally sort of could answer whatever he wanted to the query. So we'd like him to somehow commit in advance to this matrix. So we're not in the cryptographic setting, so we can't just commit in a cryptographic sense. So let's try to do something information theoretic. And the most naive idea that comes up is the following. So let's take all of these PCPs and add them up, say mod 2. Okay, so some let's call this a checksum of the PCPs. Okay, so we just added all of these PCPs up. Okay, and I'm going to call this is a checksum, so I'm going to call it C. And so the prover computes this checksum, just adding up the PCPs, sends it over to the verifier. Okay, so I'll just denote this by C.
This is the 1 times k you are going to.
Sorry?
That's the k you are going
This is poly m. Right, so the length of the PCP is m.
That's where you are sending 1 instead of k.
Exactly.
Please.
Yes.
You
Yes.
are saving the k.
Yes. Yes.
That's why k will be additive.
Yes.
What?
So the naive solution is like sending all of this over, which would be k times m.
Okay.
And then rather than that, I'm sending just like one row, which is of length m, so saving a k factor. Okay, so I sent over the checksum. And now I just do what I did before, right? So the verifier generates the PCP queries, specifies them to the prover. The prover looks at these columns, answers back. And the verifier checks that the PCP verifier accepts. Now we also want to use this checksum that we have. And we can actually use it in a meaningful way, right? So we got these columns. And the prover previously specified this checksum. So we'll just add up this column, see that we get the value here. Add up this column, check that we get the value here, and so forth for all the queries. OK, so that's a second try. And so this is not going to be sound in general, but it will lead us to a good solution if we make 2 very serious relaxations. OK, and then later on we'll see what to do with them. So the first relaxation that I want to make is to assume that only one of, so we're talking about soundness, right? So the soundness, the entire input, which is x1 up to xk, is not in the language L, or not in the k copies of the language L. Now I want to assume that only, the reason for that is that only because one of the inputs is not in L. All the other ones are in L. I don't know which one, but that's the situation. Intuitively, at least, this is the hardest case, right? So In particular, if the verifier chose at random and just checked 1, then he likely wouldn't catch that.
Yeah, but not really, because the C gets screwed up if you only assume that it is 1.
Sorry?
So this.
Right, it helps me. It helps me, but I mean intuitively.
Because of the C.
Yes. Yes. The second relaxation is going to be the more sort of dramatic one. So I'm assuming the cheating prover is behaving in a particular way, right? So when I ask the prover to send over the answers to the PCP queries, I want to assume that in all the rows, other than this bad row, which has the false statement, he's going to answer according to the unique correct PCP, according to the correct PCP. Okay, so we call this single deviation provers because these provers can only deviate on one row. I just want to point out this is sort of an abstraction. It's whenever you tell the prover not to do anything, that's exactly what he's going to do. So I don't want to assume that the prover is doing this, but at least I only want to assume this for now. Okay, so in this situation, what we have is, maybe let me go to the picture because the text is messed up. So prover sent over this, in the first round, it sent over PCP-C. Checksum C. What I want to argue is that this checksum, in a sense, really commits him to a PCP for the false statement, right? So what would that PCP be? Just take C and XOR C with the correct PCPs for all the other statements. And that defines an alleged PCP for the false statement. The thing is that once I check the consistency over here by summing these up, it means that the answers that the prover gives on the columns have to be consistent with that PCP that he committed to in the first round. Because the PCP has soundness, the verifier is going to reject. Does that make sense? OK. All right, so we have a PCP for the J star row. And the fact that we check this consistency of the columns gives us soundness via the soundness of the PCP. OK, so that's great, but we want to get rid of these single deviation provers. We want to handle arbitrary provers. So the way that we're going to do this is by using a more elaborate commitment. Rather than just adding everything up, we want to do something a little bit more sophisticated. And the technical tool that we use to do that is an encoding, E, which takes something that looks like a column from the previous slide and shrinks it up into just D bits. Think of D either as square root of K or even smaller, polylog K. We're going to play with it. But D is much smaller than K, so this encoding is shrinking. And it has the following property. So for every 2 inputs that are sort of not the same but are at distance D, the encoded values are different. OK? And it's not difficult to construct these type of things from error correcting codes. In particular, if you take E to be a random linear map, you'll get this. But we can do this also deterministically. OK, so we want to use this more elaborate tool. The way that we'll use it is we'll look at our KPCPs. And now we'll just go column by column encoding them into a checksum matrix. OK, so first column, second column, and so forth. Just encoding each column. This entire matrix, just in terms of its dimensions, is going to be something like D rows, a little bit more than D, and say poly-M columns. OK, this is our new checksum C. And again, we're going to send all of this over to the verifier, so we're paying here. We're paying D times poly-M communication. In particular, we don't want D to be too large. OK, good. So now we repeat the previous protocol. We just generate PCP queries. They specify a subset of the columns, Q. The prover sends over these columns. We check that the PCP verifier accepts all K. And now the consistency is checking that for these columns that we just got, if we encode by ourselves using this code E, we get the values that we're committed to in the first round. OK, does that make sense? OK. OK, so what about soundness? So let's think about the cheating prover. What options does it have? So one option that it can do when opening up the PCP answers, this AQ, one thing it can do is to deviate on less than D of the rows. By deviate, I mean send answers that are not consistent with the actual PCPs. So intuitively, in this case, if it's less than d, because our checksum was of size d, just intuitively from before, we should be OK. We'll catch that. And tomorrow in my talk, we'll do this more formally.
So this deviate is in two senses, both that, at most D are bad PCP proofs, and it is allowed to give inconsistent answers only on these proofs.
So for now, I want to assume that there's only one false statement.
You are still assuming
Yes,
there's one false statement?
yes, let's do that. I think it's easier to do different. So one false statement, and let's look at the deviation versus the honest PCP. Is it on more than d or less than d? If it's less than d, because our checksum had size d, intuitively, we are OK. Now, the interesting case is, what if the prover deviates on more than d of the rows? So it answers in some way that makes the PCP verifier accept, but is not the actual correct way, even though these are true statements. So that means that its answers, the answers that it's sending, are inconsistent with the unique PCP on more than d of the rows. OK? So here I'm using the fact that there's a notion of the unique PCP, because this is a UP statement. OK, so suppose that this is the case. So it's now really sending more than d rows on which it's lying. The question is, how can we catch him lying? The idea is the following. Let's choose, say, k over d of the statements at random, and ask him to send the entire PCP for those statements. Because it's cheating on more than d statements, with high probability I'll catch, or I'll do this O of k over d times. With high probability I'll catch a row on which he's lying. This row is a true statement, but he sent a wrong, he sort of committed himself to wrong PCP answers for that statement. Now when he's forced to send, to open up the entire PCP, because there's only a unique single PCP that he can send and I'll accept, I'll reject because it's inconsistent with what he sent before. OK, so let's see this in the protocol. So we have all these steps that we had before. So we send over C, the checksum. We ask for the columns. He sends back the columns. Now the verifier chooses a random subset of size k over d, tells the prover what it is, and the prover opens up the PCPs for this subset. What you check is that these PCPs are the unique correct PCPs, and that they're consistent with the answers that he had over here.
So it's important that this is done afterwards, right?
That what is done?
That is consistent, like that you ask for these rows after he already sent you the
Yes,
checkdown.
yes, yes. It's crucial. Yes. OK, so that already gives you a non-trivial amortization. If we try to look at the complexity that we get, so what is the communication? So sending over this relatively large checksum was d times m, roughly. Then all of the PCP business is roughly k. And then we selected a random k over d. I guess I have this. We chose k over d of the rows. And for them, we opened up the PCP entirely. So that's k over d times poly m. So if we set, for example, d equal to square root of k, we get these type of parameters. So square root of k poly m plus order k, rather than the trivial k times m.
Yeah. I think what you showed is enough also if there is more than one input not in the language.
Right. Right. So if they're up to d, so we'll say this formally tomorrow, but if they're up to d inputs not in the language, the same argument will work. If there are more than d, just the fact that we chose at random k over d will catch a false input. Yeah. Yes. But the argument kind of was good as long as OK, never mind. I agree. OK, so that gives sort of a square root k amortization. How about getting better amortization? So what did we?
Here,
The PCP, the witness.
the X.
The witness, no, the W.
What was the question?
But it's a PCP, not a PCPP. I'm somewhat confused.
What was the question?
What's unique here? The PCP?
The accepting witness. So it doesn't. So if we were in a situation that we didn't have unique witnesses.
So the PCP's every row is unique here?
So if we're in a situation where we were in general NP statements, now when the prover here needs to open up these PCPs, he can sort of, he's an unbounded cheating prover. He can try all possible witnesses. Each witness gives him a different PCP, and it may very well be the chance that for some of these PCPs, you can come up with, like, out of this choice of all of the possible PCPs, all these are accepting PCPs.
Yeah, I understand. It has many options.
Yes, it gets a lot of options, and
What I don't understand is even if there is one witness, we know that there is one.
No, but it's
Oh, we use it
Yes.
as deterministic?
Yes.
Yes.
Okay.
yes.
Okay.
Yes. In fact, alternatively, you could ask.
But still, it doesn't have to embed the witness, right? It doesn't.
Yeah, so it can be cheating or not, but if it's correct, then it's unique.
So we're assuming something about the PCP here, right?
I guess maybe that it's generated deterministically.
From the witness.
Yes.
Yeah.
In particular, you could ask him also here to send the witness.
Yeah.
Okay.
So you could ask him to send here also the witness.
Oh, okay.
Right.
Right.
And just assume that it's encoded
The
inside.
PCP takes a witness and compiles a proof and
Yes.
sends a witness and
Yes.
unique witness plus a proof.
Yes. Okay, so that was the complexity. But this is a square root of k. I wanted to show you a polylog k. And the idea to do that is the following. So after we chose, so we're going to do the same protocol except for the last two steps. So we chose this subset S of k over d of the rows on which we want to sort of do something. What do we want to check on these rows? So for one thing, we want to check that they're in the language, these rows. But we also want to check consistency with this AQ that he sent before. So we want to check that the PCP is corresponding to these rows at some particular subset of locations. This subset Q is equal to a particular sequence of values that the prover committed himself to. So this is what we want to check for these guys. So what we notice is that these statements are themselves UP statements, right? So there's a unique proof. Basically, the original unique proof is also a proof for these statements. So what we can do now is just recursively run an amortization on k over d statements. Okay? We need to be a little bit careful because if every time we do this we re-encode using a PCP, the length is going to blow up, which is not so good. So, but a nice observation is the fact that the same PCP that we used in the original round is still a good PCP after we recurse. It just has a little bit higher query complexity, right? So not only do we want to check correctness, which say was 3 queries, we also want to check the 3 previous queries. So it has a slightly higher query complexity, but that's something that we can afford. So, but we'll get back to why this is an issue.
Do you use your PCPs?
Yes, I mean, I'm using this.
The metrics say.
So put differently, I can assume.
The checksum you need to reuse.
No, I'm not reusing the checksum. I'm
What do you mean the original?
So the naive way to do this is sort of I choose k over d statements and to recurse on them. So each one of them, the witness for each one of them, you could take 2 options. One witness for them is the original witness that you had for the statement. A different one is this pi I, which is also like maybe in some sense a better witness, right? So if you use this pi I and you re-encode it with a PCP, so it's going to be like a PCP of a PCP of a PCP of a PCP, which is no good. So the observation is that you can just use sort of the original witness or use the same pi I that you had in the beginning as a PCP also in the recursion. But the number of queries for these PCPs is increasing.
The number of columns, I guess, to blow up in your matrix?
Yes, it will, but relatively gradually.
Okay.
So it's not too bad.
To set another C prime.
Right. When I recurse, you do a new C prime.
Okay, yeah.
Just observation is that you can use the same PCP strings, the same pi i's that you had before.
To a submatrix of the original
Exactly.
matrix A, and you run the same.
Exactly. But this is going to so this is not an issue when doing amortization, but because we want to do this to construct interactive proofs, it suddenly becomes an issue because we're doing a lot of amortizations. So, but we'll get back to that. Okay, so just to redo the statement. So using this type of recursion, we can get the following parameters.
But this is not direct sum for NP, right?
It's for UP.
An NP and UP, you take an UP and you get an IP.
Sure.
Can we get an N?
From UP to UP or from NP to NP.
Yeah, from UP to UP.
So there was this question of compression. There was these works of Juker, but I don't recall.
It's like a compression.
Is it exactly? I'm not.
I think
It's that problem exactly.
It's exactly
compression.
what?
The problem of compression of your several,
Yeah.
hundreds of instances you want to compress.
Okay, but how about IP to IP? This is probably easier.
So I expect that it should be possible. We don't know how to do this. We know how to do this for a special type of IP.
Oh, UIP.
Yes,
whatever.
yes, for that we can show it.
You know.
From UIP to UIP.
Okay.
Yes.
And you probably thought about the reduction from MP to UP.
Right. That doesn't work as is.
Doesn't work as is.
Yes. But
Because you're losing the success probabilities.
it's in a sense, I guess. Just the fact that that reduction sort of takes a witness and boils it down to a few witnesses out of which only one.
Exactly.
Yeah.
This is what
Yeah.
you're trying to
Use
The variant Vasilan.
but you're trying to make it to do the same for non-unique.
Yeah, non-unique
Yes.
you can reduce to unique in a sense. Right?
But that would work if you had like a guarantee on a bound on the number of witnesses.
Yeah.
But do you suspect that it's possible? I think I asked you that.
Just in terms of a belief, I think so. I don't have evidence.
Okay, but you don't know that this would imply one-way function or something.
No. But in a sense, this I haven't defined it yet. But the unique thing for IP is in a sense somehow like a lot of our interactive proofs are already of that form. So in particular, if you don't care, I think if you don't care about the efficiency of the amortization for IP, retaining the efficiency of the prover, I think you can prove general amortization for IP. I'm not sure. You need to think. So I would want a general amortization for IP. I would want it to retain, if you start off with an efficient prover for the original statement, you do amortization. I would want the new prover to be also like as efficient times k, roughly. If you don't have that requirement, then maybe you can show using our techniques. In particular, you can't show it because it also wouldn't preserve the rounds. So you can transform any, I haven't defined it yet, but any UIP into an IP. But it will cost you the prover efficiency and the number of rounds. This is just because the IP equals PSPACE protocol gives you UIP, which I haven't defined yet. OK, so let's move on. So far we were talking.
Can you go on?
Yes.
To get these parameters, you really choose D to be like a constant and do it log k times and
not a constant, but maybe polylog.
but something very small,
Yes.
not like square root.
Right. Exactly. Right. So because we had to pay D in the first round, but now we care less. So if D is polylog k, we pay the polylog k, fine. But now we shrunk to k over polylog k, which is a great situation. It's good enough for us because we'll do the recursion log k times and we're fine. OK. Great. So far we were talking about amortizing NP or UP statements. But to get our constant round interactive proofs, we need to be able to amortize interactive proofs. As I said, we can do it. Generally, we'll need a special type of interactive proofs. Or basically, just like in the non-interactive case, we needed a notion of uniqueness. We're going to need the notion of uniqueness or we're going to call it unambiguity for interactive proofs. We'll define that in a second. And we also need a notion of PCPs for interactive proofs. Right, so we strongly use the PCP theorem. So we need some notion of a locally or probabilistically checkable interactive proof. So let's define these notions, which I think even are interesting in their own right. So what is an unambiguous interactive proof? Remember, this is the analog of UP for interactive proofs. So the idea is the following. So we have an interactive proof. It has the standard completeness and soundness requirements. In addition, I want an unambiguity requirement, which says that if you take a statement X that is in the language, and you run the interactive proof for it, so the interactive proof is specified, and at some point the prover decides not to send the message that it was supposed to send according to the interactive proof specification. If he does that, then with high probability over the verifier's remaining coins, the verifier is going to reject, even though this is a statement in the language. The fact that the prover at some point deviated makes the verifier reject. And one nice protocol that has this property is the sum check protocol. So if you recall in the sum check protocol, the prover keeps sending these polynomials over to the verifier. If you think about it, if at any point the prover specifies a wrong polynomial, then it has to be, because these are low degree polynomials, they have to be very far apart. And it's pretty easy to show, in fact, the usual, I think, analysis of the sum check protocol shows that if the prover at any point sends a wrong polynomial, then the verifier is going to reject. Okay, so the classical sum check protocol, the IP equals PSPACE protocols, they're unambiguous. And the second thing that I wanted to note is that this class UP is basically a restriction of unambiguous interactive proofs in which the prover just sends a single message and the verifier is deterministic. Okay, so this is just a generalization. So that's the notion of uniqueness or unambiguity that we need. Is the battery dead? I have a lot of technical difficulties.
IP equals UIP, right?
Yes, but that statement kind of ignores a lot of things, like what does this transformation cost you? But yes, that was sort of maybe my possibly wrong intuition to your question about amortizing IP. Okay, the second notion that we need is a notion of PCPs for interactive proofs. So the notion is the following. So it's going to be just a standard public coin interactive proof. You run we call it a public coin interactive proof. All the verifier does is just send random coins over to the prover. Doesn't do anything else until the end of the protocol. Now we're going to add a requirement that at the end of the protocol, all that the verifier needs to do is to look at a few locations in the transcript. Actually, we'll need to look most likely in each individual message, but at only a few locations in each message to decide whether to accept or reject. Okay, so that's we call this a probabilistically checkable interactive proof, a PCIP. And if you think about it, the one-round version is exactly the notion of a PCP, right? It's just the prover standing over one message. The verifier just looks at a few locations and decides whether to accept.
They are talking, but then
so it's a regular public coin interactive proof, right? So the verifier chooses random coins, sends them over to the prover. Prover sends a message. Verifier tosses coins, sends a message. Prover sends a message, and so forth. But at the end of the protocol, when the verifier needs to decide whether to accept or reject, it will at random look at few locations in the transcript.
So there is no one activity in here. You can run the rounds in parallel. Why don't you?
You cannot run the rounds of the sum check protocol in parallel.
Yes.
This is new randomness, but it's independent of whatever.
Yes, it's no randomness. Yes.
I think probably understanding is not just so during the conversation the verifier looks at everything.
He doesn't look. He doesn't. All he needs to do is just send random coins. It's a public coin protocol.
Responses. It's just random
So what does he
queries.
do?
with no
This notion doesn't make sense if it didn't have public coin written here. But public coin means that all that the verifier needs to do during the interaction is choose random coins and send them over. It doesn't depend on the messages that he got.
Okay.
Right? So throughout the interaction till the end, all the verifier does is toss coins, send them over. Toss coins, send them over. He's getting a bunch of messages. He keeps them in a buffer or whatever. And then at the end,
But if it's public coin, why should he send them?
Well,
because public coins are useful.
Control the heads of the prover. Think about the sum check.
Right, so public coin protocols are useful. Maybe.
It's queries. This is the questions he wants the prover to answer to.
Okay.
It sends like private randomness over. It's not because the prover is lacking randomness. This is the query.
Okay.
So if you think of okay.
These bits that he reads are chosen randomly, right?
Yes, after the interaction.
Then you can do
Yes.
any protocol. Just at the end,
Sorry?
also he says the decision.
Are you asking about a transformation from interactive proof to?
Yeah.
So first of all, we show this. It's not very difficult, but I'm not sure what you were saying.
No, I'm asking so the way you're defining it.
Mhm.
So these bits, these few bits have to be chosen randomly.
Yes.
Because
Yes.
otherwise.
Yes. And
PCIP.
okay, so that's a probabilistically checkable interactive proof.
There will be many of these, and you'll sum them up in a similar way, right? And there'll be, these buffers that
Yes.
are created by this, there will be many of them.
Right. To do the amortization, exactly.
It's only weird because of the fact that you are not actually looking at the messages from the prover.
Right.
Never. You'll just look at.
Right, you're just storing them.
Sample that, yeah. So where are they here?
Yes.
They are actually stored. Some of them.
Yes.
But
Yes.
it's just in some sense it's it's a thought experiment because you'll sample from.
Right. So in particular, if you think about it, as usual, the running time for this verifier, just getting the messages, is long.
Exactly.
So if you want to think of it as an abstraction, we don't count the running time for that, or you can think about it as a weird model that maybe is useful.
You will not count the running time because you get an encoded version of this, which is much shorter.
Right.
That's the only thing that you.
Right.
Yeah.
Right. Okay, so I should mention that this is related to, but different from, a notion of interactive PCPs, which is a notion of that Yael and Ran had. That's a PCP that you can interactively check. Here we have an interactive proof that you can probabilistically check or locally check.
For any computation there.
I think we covered all. I think probabilistic.
IPC.
Yes. Yes. And then we also need. You're still here?
No, the last one.
The last one? Why? Is it?
No, because now it's even more.
Right. So we need a combination of both of these notions, of the unambiguity and the PCIP, which really seems to be weird, right? Because we want to, if the cheating prover, say, sends a message but only changes it at 1 bit, how will this verifier ever notice? So we need to do to be careful about the notion, but we have a notion that is very useful for us. And this is the type of things that we can amortize. Unambiguous PCIPs. Okay, so I'm almost done. I just want to kind of briefly recap what the high-level protocol was for getting the constant round interactive proofs. So what we wanted to do, recall for the recursion, this outer recursion, is to assume that we have whatever type of interactive proofs are good for us for small computations of length t. And we want to construct, using amortization, the same type of interactive proofs for computations of length k over t. We do this using the amortization. So the prover specifies the k intermediate locations. And then we have, because we have interactive proofs for these short computations, we can amortize over them. One crucial thing that we need is that the amortized interactive proof still has these two properties, that it's unambiguous and that you can locally check it. And one thing that turns out to be a problem is that, as we said, the amortization increases the number of PCP queries. If you just care about amortization, it's not too bad. Because we want to keep doing this in this outer recursion, it turns out to be a lot. So we have an additional step, which is sort of a query reduction transformation for PCIPs. You can think about it more generally, or less generally, as a transformation taking an interactive proof and transforming it into a PCIP. And then the way that our interactive proof is constructed is by sort of interleaving amortization steps. After each amortization step, we do a query reduction, then another amortization, and gradually we get interactive proofs for longer and longer statements until we get sort of the entire thing that we wanted. OK, so just to recap, we got constant round interactive proofs for these bounded space computations. We have a bunch of these new notions. So this notion of amortizing IP and NP proof systems, this unambiguous interactive proofs, probabilistically checkable interactive proofs. And I'm going to talk about all of this in more detail tomorrow. Some interesting open questions. So one question that I think is really interesting, it also has a $100 cash prize from Yad Kalai, is to get a version of the IP equals PSPACE theorem where the prover is relatively efficient. What do I mean by that? So maybe a different way to put it is proving as easy as computing? Okay, so can we, in general, you would expect that maybe, or hope that if you want to do an interactive proof for d time space ts, you'd get a prover that runs in some poly t or even t time. And our protocol doesn't get that. The classical IP equals PSPACE protocol gets a prover that runs in 2 to the poly s. So very inefficient prover. And this is a great question.
What do you think about what will be your projection for the verifier, prover and verifier?
So the verifier should be poly s, polylog t.
Poly S, polylog.
Um,
And prover poly S.
Poly t. Yeah, poly t and I mean poly s dominant. The poly t dominates the poly s. Yes. So that's one question. The second is, so we have only amortization for UP statements. I think it's just interesting by itself to get amortization for NP. And as for our constant round interactive proofs, The number of rounds is exponential, and this 1 over epsilon would be great to improve that. The dependence on the space, the fact that we get n to the delta for a sufficiently small delta, I actually don't think it's that small of a delta. And there's hope to get it up to close to 1 or something. So that would be really close the gap between the upper bound on doubly efficient interactive proofs and what we get. Yeah, and I think that's it.